All right, so now let's continue to talk about alkanes, but specifically the properties as well as reactions. So first of all, in terms of classifying alkanes as either gases or liquids, we have this sort of cutoff rule that we use. Alkanes that have 1 to 4 carbons are gases at room temperature. So methane, ethane, propane, as well as butane are gases at room temperature. Specifically, propane and butane are used as fuels commonly, right? So your grill is likely powered by propane. They have lighters that are powered by butane. These are very often used as fuels. When we get from 5 to 8 carbons, so pentane, hexane, heptane, and octane, these are liquids, but they're highly volatile liquids, meaning that they enter into the gas phase really easily. They have a really strong odor associated with them. That also makes them very useful as fuels. You know, kind of the benefit of a gas versus a liquid. Using a liquid is sometimes considered to be more beneficial because it's much more compact. So transporting it would be easier. That might be one consideration that you would be using. But again, those are liquids and specifically highly volatile liquids. And then when we get to longer than that, you know, so let's just say anything above that is going to be a liquid with a higher boiling point. So another way of saying that would be a non-volatile liquid. These can be used as fuels too, right? So anything can undergo combustion, but nonetheless, they're not quite as volatile as the other ones. If you get even bigger than 16 or 17 carbons, now you get into solids, okay? So these would be waxy solids at room temperatures. Okay, so yeah, kind of like you can think of like candle wax or something like that would be composed of a really, really, really long carbon chain, right? So if this is decane here, right, all with 10 carbons, let's just draw 18 carbon chain so you can see. So now we have right? Something like that. So a really, really long carbon chain, yeah, would be something like a wax. All right, and then once we get to as long as 25 or above, these are also solids, but quite viscous, something like a Vaseline or a petroleum jelly. Okay, so right, our really small alkanes are gases. In the middle there are liquids, and then as we get longer, those are solids. Those properties all relate to what would be the boiling or melting point of those compounds, right? So its state at room temperature reflects its boiling and melting point. And so the trend here is the boiling point of these compounds, so the point at which it goes from being a liquid to a gas. If it's really, really low, that means it's going to be a gas at room temperature, right? Whereas if the boiling point is higher than room temperature is somewhere around 20 degrees Celsius. So if its boiling point is higher than room temperature, then that means that it's a liquid at room temperature, okay? And so the trend that we sort of have been explaining here is that as the number of carbon atoms increase, the boiling point of those compounds increase. Okay, so that temperature at which it goes from liquid to gas will get higher and higher and higher the more carbons that you have. Okay, this is because of what's called dispersion forces. You know, we're not going to go too much into that. Let's just say that the way that these molecules stick to one another is easier the longer it is. Right? So methane can't really stick to its neighbor very much, but something like pentane that has a lot more surface area can stick to its neighbor a little bit better. Okay, now let's talk about what the effect that branching has. Okay, so first of all, we have 1, 2, 3, 4, 5, 6 carbons all in a row. That would be hexane. These linear molecules don't have any branches on them. Versus if we look at something like this is now a branch in this molecule here. You have a carbon that's bound to 3 other carbons. Okay, so these are considered branched alkanes. We don't know how to name these yet. This is 3-methylpentane. We don't know how to do that yet. But if we're going to compare molecules that have the same number of carbons, so notice that this molecule here is actually, so this was hexane in pink. This molecule here, which, you know, again, we'll learn how to name them in the next lecture. We don't really know that yet. But this also has a total of 1, 2, 3, 4, 5, 6 carbons. Right? It actually has the exact same formula. These are both going to be C6H14. Same formula. The difference is that they're not just connected in a line. There's this branch point. And then we have this other example here. Dimethylbutane, which again contains 1, 2, 3, 4, 5, 6 total carbons. It again has this same formula. So the difference between these is we're increasing the number of branch points that this molecule has. And look what that's doing to our boiling point. So our linear molecule has the highest boiling point. The more branches we add, the more we lower the boiling point. Okay. So the trend here, and I hate that this arrow is pointed the same way it is on the other side. It should be pointed the other direction, but whatever. Is that as we increase the number of branches, we decrease the boiling point when we keep the number of carbons the same. And the last sort of trend in boiling point we're going to talk about is what happens when you have a cycloalkane. They will have a boiling point that's higher than their straight chain counterparts. Okay, so let's look at a bunch of 5 carbon compounds here. We have pentane has a boiling point of 36. When we take compounds that have the same formula, C5H12, whoops. But we add branch points in there, we decrease that boiling point. And if we, instead of having pentane, we have cyclopentane, we've increased the boiling point relative to pentane. Okay, so branching decreases the boiling point. If it's locked in a ring, it will increase the boiling point. All right, so those boiling points really the main property that we're going to talk about when we talk about comparing alkanes. I expect you to know trends in boiling points. So if I like give you 3 molecules and I say rank them by increasing boiling point, that would be an example of something I could expect you to do. I could have given you like these 4 structures here and said, put them in order of increasing boiling point. That would be an expectation that I have after this lecture. Moving on to reactions. Again, the main reaction that we talk about when we talk about alkanes is the combustion reaction. And a combustion reaction is a very specific type of reaction where we take our alkane, a hydrocarbon, combine it with oxygen gas, and it produces carbon dioxide and water. Okay, these reactions are used through like very widely throughout the world because they also generate a crap ton of energy. That's why we have this global warming crisis right now, is dumping a whole bunch of CO2 into the atmosphere, because the main way that we as humans have been able to generate power, generate energy, is by utilizing this combustion reaction here. Okay, your car is, if you don't have an electric vehicle, is being run by a combustion engine. This reaction is happening over and over and over again under the hood of your car in order to produce the energy that's driving you forward. Okay, but again, it's hydrocarbon plus oxygen gas gives you carbon dioxide and water. the hard part, the skill that I'm going to expect you guys to have is to be able to write these combustion equations given an alkane, meaning that you're going to have to be able to write some sort of a balanced chemical equation. Okay, and I'll show you the way that I do this, might make it easier. But one thing to just note, right? We have methane, our simplest alkane that has one carbon. That's only going to react with 2 equivalents of oxygen to produce 1 CO2 and 2 water. Whereas if we have, the more carbons that we add, so for example, we go up to propane with 3 carbons, now we're consuming 5 oxygens and producing 3 carbon dioxides and 4 waters, right? So the longer your hydrocarbon, the more oxygen that's going to be consumed, the more carbon dioxide and water that's going to be produced, and actually the more energy as well. So the energy that's produced is larger for longer hydrocarbons. Now let's get into balancing this here, okay? So again, you're gonna have I'm gonna ask you something like, write a combustion equation for butane. So you're gonna know you have to start with butane. And then the reactants are always the same. It's just oxygen's the other reactant. And you're always producing CO2 and H2O. You can write energy if you want, but we're not quantifying the amount of energy produced. So that's kind of just an aside. We're not going to focus on that. The real question here is, how do we balance this chemical equation? Okay. The strategy that I would suggest is you're going to ignore oxygen until the last step. It's actually easier to balance the carbon dioxide and the water first, and then go back and figure out O2. Okay, these equations aren't too bad to balance, and the reason is because all of the carbon that's over in our hydrocarbon will eventually go into CO2, right? So right off the bat, I can sort of balance the carbons in this equation by putting a 4 there. Right now I have 4 carbons over here and 4 carbons over here. Let's just remember that that's what we're doing when we're balancing our chemical equation. I'm going to make sure that I have the same number of carbons, hydrogens, and oxygens on the right-hand side as I do on the left-hand side. That's what we're doing when we're balancing. Likewise, I can balance the hydrogens fairly easily because all of the hydrogen in my hydrocarbon will end up in water. So if I have 10 hydrogens in my hydrocarbon, I would need to produce 5 waters, right? Because remember, each water contains 2 hydrogens. So that brings me up to 10 hydrogens over here and 10 hydrogens over here. All right, now that I have those 2 balanced, I can work backwards and figure out how much oxygen. So for CO2s, this would be 8 oxygen atoms altogether, right? Because for CO2, each carbon dioxide molecule has 2 oxygens, so 4 times 2 is 8. Likewise with water, each water has 1 oxygen, so that would be 5 oxygens total. So that brings me to a total of 13 oxygens. Now, the only problem is that oxygen gas is diatomic, meaning that it's not just O all by itself, it's O2. So in order to balance my oxygens, I would have to have 13 halves over here. The real kicker there is that you always have to have whole numbers in your balanced chemical equation. That's okay. That's really easy to do once we've gotten it to this step. I'm just going to, well, so real quick, let's just note that I indeed have 13 oxygens over here too. So numbers of carbons are the same, hydrogens are the same, and oxygens are the same. So everything's balanced. The only problem is I have this fraction here, which isn't legal. So I'm going to have to make that a whole number. That's actually really easy to do. Let me clean this up a little bit. All you're going to do is take this whole thing, the entire equation, and multiply it by 2. So that is, take each one of those coefficients and multiply it by 2. So my balanced chemical equation will be 2 butanes plus 13 oxygen gas gives me 8 CO2 and 10 waters. That is a balanced combustion equation for butane. So I expect you guys, I could give you any hydrocarbon in the world and you should be able to write me a balanced chemical equation. Okay, cool. Just some other properties about alkanes. We actually kind of talked about this when we were talking about organic chemistry in general, but they are nonpolar. Because they are nonpolar, they are insoluble in water, and they're also less dense than water. Okay, what that means is that they'll actually float on top of the water. And they are, as we said, they're flammable, meaning they undergo that combustion type of equation. Alkanes, I mean, I guess this is more or less a property and more of like a fun fact. They are what is found in crude oil as well, right? And that's why when you spill, you have this big tanker out in the middle of the ocean that spills a bunch of oil, it will float on top and not sort of dissolve and be dispersed throughout. And that's because it is less dense than the water and it's nonpolar, so it's not going to mix in there.